Hello everyone, I'm Adam Huang from Indiana University. I'm thrilled to present a groundbreaking work from the Quantum Cognition program, the Quantum Sequential Sampler model. To those who are unfamiliar with quantum cognition, our program models human cognition using quantum probability theory, without assuming quantum physics in the brain. I'm honored to share my contributions alongside Dr. Jerome Busmeyer from Indiana University and Dr. Emmanuel M. Poffels and Zoe Ebelt from City University of London. Thank you very much for your interest in our work. So what research question does the quantum sequential sampler resolve? Empirically, we found that humans' judgment tend to violate basic axioms of probability theory. A famous example is the conjunction fallacy found by Tversky and Kelman, where participants judge the probability of Linda being a feminist and a bank teller to be greater than the probability of her being a bank teller. This is a fallacy because in classical probability theory, events are modeled by sets. As shown in the picture here, the intersection set of feminist and bank teller must be within both the feminist and the bank teller sets. Thus, the probability of this intersection must be smaller than both the feminist set and the bank teller set. Despite people's probability judgment violates probability theory, empirical studies also found that we are surprisingly rational. Costello and Watts found that despite people making mistakes in some probability judgments, they tend to follow most of the rules of probability theory as well. Besides, many cognitive processes are very well explained by Bayesian theory of cognition, a theory which obeys probability theory. This thus leads to our research question. How can we build a computational model based on rational analysis to explain these empirical violations of probability theory? It turns out that our quantum sequential sampler model provides a way to address this question, which we will discuss later in the presentation. Before delving into the details of our quantum sequential sampler model, let's first explore the empirical study that forms the foundation of our research. This study represents the most extensive dataset of probability judgments to date, involving a remarkable 1,178 participants. The survey was conducted a few months prior to the 2020 U.S. presidential election. The questions posed in this study revolve around the election, specifically regarding the likelihood of the two candidates winning specific states. As depicted on the slider here, participants were tasked with indicating their responses by sliding the marker. An example question would be whether Biden would win Nevada and Trump would win Georgia, as shown in this picture. During our empirical study, we found that the majority of conjunction and disjunction questions posed to participants resulted in a fallacy. To clarify, the disjunction fallacy here refers to the erroneous judgment of a disjunction, let's say probability of A or B, being less probable than one of its components, probability of A and probability of B, which clearly contradicts the principles of probability theory. Moreover, our study identified violations of probability identities as predicted by Zhu et al. 2020 and Costello and Watts 2014 within our dataset. These identities represent fundamental relationships among probabilities that must sum to zero. We will discuss these identities with more details later in this presentation. Another notable finding from our empirical study revolves around the cognitive reflection test. This test is designed to assess whether participants are inclined towards intuitive judgments or analytical judgments. A higher CRT score indicates a greater propensity for analytical reasoning. In our investigation, we made a remarkable discovery. The percentages of conjunction and disjunction fallacies exhibited a linear relationship with the participants' CRT scores. This finding provides valuable insights into the connection between cognitive reflection and the occurrence of probabilistic fallacies, which we encourage future research to explore. After this overview of the empirical study, now let's turn our attention to the quantum sequential sampler model. To optimize our time, I will only provide a conceptual overview of the model, omitting the intricate mathematical details. The model comprises two key components, the quantum probability part and the sequential sampling part. The quantum probability part represents subjective probabilities, capturing the nuanced nature of human judgment. These subjective probabilities serve as inputs to the subsequent sequential sampling process. The quantum probability part of our model holds the key to explaining the occurrence of conjunction and disjunction fallacies. In quantum probability theory, the evaluation of conjunction and disjunction events follow a sequential process. Interestingly, the order in which these events are processed can yield different results. This phenomenon is captured by the interference or order effect term in our model. The order effect terms or interference terms empowers the quantum model to generate conjunction probability that surpass the individual probabilities of the events involved. When this interference term is set to 0, the model aligns with classical probability theory. And when it is non-zero, the model becomes a quantum model. Now let's turn our attention to the sequential sampling part of a model. The sequential sampling part of a model utilizes a constant drift rate Markov model, which follows the Kolmogorov forward equation. In order to employ this model, we need to specify two key components, the initial state and the intensity matrix K. Here is how the intensity matrix K is defined. In the equation below the matrix, PA means the subjective probability for an arbitrary event A. Alpha is the drift rate parameter, and C plus and C minus represents a pair of additive bias parameter that represents over and underestimation biases. When C plus is greater than C minus, we have an overestimation in probability judgments, and when C minus is greater than C plus, vice versa. Since only the difference between C plus and C minus matters in Markov models, we combine C plus and C minus into a single parameter K when fitting the models. Finally, I introduce how the initial state is defined. Conceptually, the initial state is defined as a symmetric beta distribution discretized to integers from 0 to 100. The reason for this discretization is that in our empirical study, probability judgments are measured as integers. The use of this symmetric beta distribution is consistent with the Bayesian pair used in the Bayesian sampler model in Zhu et al. 2020. If you would like to know more details about the model construction, please come to the discussion section at 4 p.m. on June 22nd Eastern Time. To provide an overview, here are some theoretical advantages of quantum sequential sampler. First, quantum probability provides axiomatic explanation of conjunction and disjunction fallacies. In other sampling-based models, conjunction and disjunction fallacies are explained either by assuming they are more noisy than marginals when sampling, or more computationally expensive to simulate. These explanations are less axiomatic than the quantum explanation. Second, sequential sampling part represents a response process that generates violations of probability identities due to noise. These violations are not explainable by the original quantum probability model. Third, existing sampling models produce binomial response distribution. On the other hand, our sequential sampling process can produce continuous ones. This eliminates the need of a number rounding mechanism to the nearest integers or nearest 5s or 10s. as required by existing models. Finally, and perhaps most importantly, the Markov decision model in our sequential sampling part can predict response time of probability judgments. We compare our quantum sequential sampler model with the Bayesian sampler model by Zhu et al. 2020 using the Bayesian information criterion. The quantum sequential sampler model showed better data fit with lower BIC scores, indicating its superior performance. Additionally, we performed cross-validation generalization tests, further confirming the effectiveness of the quantum sequential sampler model in predicting both conjunctions at these junctions. These findings highlight the robustness and accuracy of the quantum sequential sampler model in explaining human probabilistic judgments. During our analysis, we examined the predictions of both the quantum sequential sampler model and the Bayesian sampler model. Notably, we observed that the quantum sequential sampler model consistently outperformed the Bayesian sampler model in capturing the empirical data. This is visually demonstrated in the figure shown here, where the predictions generated by the quantum sequential sampler model align more closely with the observed data points. Importantly, the quantum sequential sampler model also successfully captures the violation of probability identities as identified by Costello and Watts 2014, and later expanded upon by Zhu et al. 2020. This is something that the quantum model in Bosmeyer et al. 2011 cannot explain. These 18 probability identity violations are a crucial aspect of our model's explanatory power. Previous research suggests that these violations were influenced by noise, and thus can be explained by the sequential sampling part of our model. As can be visualized by this figure here, quantum sequential sampler predicts the violation of these probability identities much better than the Bayesian sampler model. Interestingly, we found that Z7 and Z8 tends to be greater than 1, which seems to also violate the original assumptions about these identities in Costello and Watts 2014. To summarize, we propose the quantum sequential sampler model to explain empirical violations of probability theory in probability judgments. A minor issue of our work is that we do not collect response time data. Thus, future work can continue to explore whether our model can predict response time distribution of probability questions correctly. And finally, here is a list of references mentioned in this presentation. Again, thank you very much for your interest in our work, and see you on June 22nd.